Ni hao, everyone. Today we're going to talk about the rest of the reviews and want to continue with how to represent other types of data like images, sound, video, and multimedia. So let's start with images. Now, since everything in the computer is stored using bits, right, that we can represent with ones and zeros, then we could say that all data in the computer has a numeric representation. That's why we used the numeric systems that we looked at. We use the binary system, the ternary, and the hexadecimal, right? So we could say that every single byte that is used to represent data may have numeric representation, right? So images are the same case, even more when we talk about the bitmaps. Now, there are two main representations of images, or two kinds. One of them is the bitmaps, and the second one is the vectors, the vectorized images. Now, bitmaps are just a grid of pixels. And what's a pixel? A pixel is just a dot of one color, and this color may be made out of the combination of shades of three colors, for example, for the RGB system. In the RGB system, we have red, green, and blue, and in other systems, we use different colors. For example, CYMK is cyan, yellow, magenta, and black. So that's another system, but one that is maybe easier to explain and to understand is the RGB. So in the RGB, we just have a combination of three different lights or colored lights in its different shades. So 0 would be the absence of red light, and 255 would be the maximum red light that we can generate in one pixel. And the same case for green and blue. So if we combine these three colors, we get the color for one pixel. So every pixel is going to be kind of like divided in three different colors. Now, the bitmaps may be also of black and white, right? I mean, we could create a file or an image file that has only black and white. In that case, the necessary occupation of bits would be just one bit, because we can have two colors, for one for white, for example, and 0 for black, right? In the same manner, we could have a grayscale. We're using 4 bits. In that case, we would have 2 to the power of 4 options, so we would have 16 colors. RGB uses 3 bytes. That means 32 bits. That means 2 to the power of 32, which is more than 4 million colors. Back in, I don't know, like 3 or 4 decades ago, the first colored screens that we used a basic color made out of 8 bits, and that made 256 colors available. Now, the quantity of bits that we use is what we call color depth, right? And that's an important concept here. Now, bitmaps, they have information obviously about the different pixels and the position of the pixels, right? That's important. In a pixel, we have a specific position and a color. But in order to know what a bitmap in total, where a bitmap file is, we need the file header, which has the information about the image resolution and the color scheme. So the color scheme might be, for example, RGB, and the image resolution is the number of pixels that we have for horizontal and for vertical lines. Okay. Now, you should make a difference between what's image resolution and screen resolution. Now, screen is the physical device, and the physical device is going to have a fixed number of pixels, right? This is, for example, a very old screen. The number of pixels that you have in the screen is fixed, right? But the image resolution is going to change between image and image, right? They are both defined in pixels, but they're not the same. Now, one thing that you should have in mind for bitmaps is that if the image resolution divided by the screen resolution is a small number, that means that the image that you have is going to look distorted, because the number of pixels is going to be less than the screen resolution, right? But if the image resolution is higher than the screen, then the information is going to be enough for it to be very detailed. So you're going to have a detailed image. Now, talking about the concept of color depth, we can calculate the bitmap size using the image resolution, which is the number of pixels that we have for horizontal and vertical, right? And with the color depth, which is the number of bits that we use. So, I don't know, let's say that if we have 1024, this is the image resolution, and we have an RGB system, then we're going to have 3 bytes, right? So the number of bytes that I'm going to have here is 3 MB bytes, right? Which is close to 3 megabytes, right? So it's important to make the difference between those two different prefixes. According to the norm and to the Cambridge curriculum, you should make a difference between the powers of 2, which is in this case, for example, 2 to the power of 10 bytes is 1024 bytes, which is called a kilobyte, which is different to 1000 bytes, which is a kilobyte. All right, so you should understand the difference. If it's a power of 2, it's talking about kivi, mivi, or kivi, and if we're talking about powers of 10, it's kilo, mega, and so on and so forth. All right, gigatera, all that. All right, now vector files are a different type of file, where what you have is vectors and descriptions of geometric objects. So you have geometric objects like circles and squares and all that, and triangles, where you define a position in the file in the canvas, which is like an imaginary workspace, and then you define where these are going to be placed. Obviously the figures or the shapes are more complicated, and you also define lines and all that, so you can create an image out of those objects, and what you have stored in the file is the commands and the drawing list that you need to make to recreate that file. Now, one advantage of that is that you can change the size of the objects because they are relative to the canvas. And another thing is that if you scale those objects, there is no distortion. So you can scale into a bigger, I mean, you can go and use like a magnifying glass in a very specific corner of a letter, and if you keep scaling up and scaling up, you're going to see the same corner. That doesn't happen with the bitmap, because as you know, that depends on the resolution. All right, Okay, guys, so I think that's the most important thing about images. We'll continue with the next section. Now, sound, since we mentioned before, we need to, everything that is data in the computer needs to be represented in bits, and it should have a numeric representation. Sound is not an exception. So what we know about sound is that a sound is a disturbance of air, of the air, in the form of waves, right? So waves are described in its frequency and amplitude. Frequency means how many times per second, right? Or cycles per second the wave is vibrating, right? And the amplitude is how big the movement is, of the movement of the air, of the molecules of the air. I'm not sure about decibels. I think it is, but I'm not sure about this being the measurement for the amplitude in sound. I think it is, but I'm not sure. So if you want to find more about it, just check what the amplitude is measured in. But I am sure that the frequency is measured in hertz. So a hertz is equal to 1 cycle per second. This is used in many other fields. And so you could describe a wave sound wave, sorry, by just describing the frequencies and the amplitudes at different points. Or if you use a time versus amplitude graph, you could see that it's just measuring the different amplitudes at a certain time, right? So if I start sampling this, I'm going to have here one for this particular moment in time, one value for amplitude, for this one value. It's just like any graph that you have seen in math or physics, right? So one thing that we know is if you hear a high-pitched sound, it corresponds to a high frequency, and a low-pitched sound is going to correspond to a low-pitch sound, right? That's a low frequency, sorry. So how do we code that? So how do we take this and put it into binary to code it into a computer? Well, one way is to use an ADC, or analog to digital converter. And what this does is takes the the sound waves and changes that into pulses or electronic pulses, and then it codes that into a digital number. And what it does is it gives you the frequencies and the amplitude, sorry, in that particular wave. Now, in order to design this, you need to define what's going to be the number of bits that you're going to use for the amplitude, which is going to determine how many of these lines I make. Obviously, if I have a bigger number of bits, I'm going to have a better quality of the reproduction of the sound. And what's going to be the bits for the samples per second, right? Or how many samples per second I'm going to get. So that's going to determine how many numbers I store here in one particular second. Let's say that this is time, and this is 1 second, second 2, 3, 4, right? So it's different if I just measure 2 numbers here, or if I measure 100 numbers in the next second, right? So that's what it's called the sampling rate, how many measurements I make in 1 second, and the sampling resolution is how many bits I use for the amplitude. All right. So obviously, if I increase the resolution for sampling resolution and sampling rate, the size of the file is going to be increased, right? And that's why we're going to talk about compression later on. Now, well, not about sound, but we're going to talk about compression for images and video. And one thing that we know is that we need at least twice the highest frequency for the sampling rate. So if the frequency of the sound is 2 hertz, the minimum frequency that I need for the sampling rate is 4 times per second. All right, I think that's enough for the sound. Let's move on to the next topic. Now, video is a little bit different. Video is, you could think that it's just a bunch of bitmap files, right? Still images there, and then you would define a frame rate, like how many times I project in the screen those still images. And that's one approach. Actually, the frame rate, which is how many frames per second I present to the screen, how many of those still images I present to the screen, is called the FPS, or the frames per second. And the human eye cannot distinguish, cannot see the difference if you use 50 frames per second is a very smooth image or video image. Now, how is the image actually made? To know that, you first need to understand how you code that into bytes. You need to understand that the video images are just made out of, you need to define how many lines per each frame you're going to reproduce in the screen. So how many of these lines of pixels you have in the screen, or you're going to show to the screen. And the second one is how many pixels you have per line, right? How many of those you're going to describe there. That's going to determine the encoding of the video in bits and bytes. Now, there are two main methods, the interlaced and the progressive. The interlaced is using this idea, is saying, okay, I'm going to number these lines, and what I'm going to do is I'm going to trick the eye, and I'm going to present, for one particular moment in time, I'm going to present just the odd lines of the screen, and for the next second I'm going to present the even lines, right? So I'm going to do that using this frame rate here, and the humans are not going to perceive any change, right? And they're going to perceive that I'm presenting not only a complete image but a smooth video, right? So that is going to divide the number of bytes to half, right? If I do this, if at one particular moment I just use the blue ones, and to the next moment I use the red ones, right? It's going to divide in half the number of bits and bytes that I'm going to use. That is called interlaced encoding. But nowadays, since we have improved in our technologies, we can use the complete image, and we can send the complete image to the screen, and that is called progressive encoding. All right, those are the two differences that you need to have in mind, and that's what you need to know about the video in general terms. Now, since we have all those bits and bytes, and we always want to save space and money, we need a way to compress, so to define some techniques to compress the information. So there are two main ways to compress things. You can use lossless compression, which means that you don't lose any information, which means that you're going to recreate the exact original information that you had, or lossy compression, where you lose the information or some of the information, so you can recreate a similar thing to the original. So when we're talking, for example, about text files, or this even works for different types of records, you can use the Huffman encoding, which is using the idea of whatever it is common in like patterns that you can find in the bits and bytes. Like for example, in the English language, the letter E is very common. Then what you do is, instead of using the complete code for E, which is something like this in UTF, letter E in UTF is 0065 in hexadecimal, which would be this 1, 2, 3, 4, right? 4 different nibbles. Instead of doing that, I'm going to say that E is going to be just 1, 0, this sequence. So if I do that, then, and if I define some patterns to recognize when I'm using the compression, then I'm going to be able to reduce the number of bits that I use for that particular character. And since this is a very common character, the file is going to be reduced. Now, another technique is the wrong length encoding that is used, for example, for bitmaps, which is the idea is to count how many times you find a pattern, and then you take that information and you compress the file. So for example, let's say that this is an image made out of pixels, and you have this, for example, this line is a green line, and this is a green line, and this is a blue and green line. So instead of storing, this has, for example, 16 different pixels, which for each color I would need 3 bytes, right? So that's going to be 16 times 3 bytes for this little and very simple image. So what I could do is I could count the number of pixels that I have here in green, right? And then I just say, oh, I have 16 green pixels, so I would define the number of pixels and then the color. So that's going to take, for example, here it's just going to have 4 bytes instead of the 48 bytes that I would have here, right? So it's a considerable, it's a very good compression if the image has big patterns. So yeah, it's the same here. So I could say, for example, this line is 5 blue, 4 green, 5 blue, and 2 green, right? So then I would have 4, 4, 4, 4. I would have 16 bytes here instead of 48. That's another way to do it. And the other one that we could do is, for example, for video. In video, we can, instead of counting the patterns, we could say, for example, oh, I'm going to track what's the difference between this frame and this frame and this frame. And I'm going to define a way to report to the video card what's the change between this and this. So I'm going to store, for example, the information for this, and then I'm going to add this pixel and then add this pixel and this pixel, right? So I only keep track of the differences. And that's something that is used for video. And when I'm talking about having the same type of file or storing, for example, a movie that has sound, image, and text, then you need to be talking about what you call a multimedia container file. So a multimedia container file is just a file that contains multiple types of media, like sound, image, and text. Alright guys, I think that's it for this chapter. I'll see you in the next one.